New paper by Nvidia shows how to pre-train large language models in FP4, just 4 bits floating point number. They achieve 2 to 3 times faster training with 50% less memory. I wrote this blog, which is easier to understand than the paper, so I'm gonna be explaining it from here, but you have URLs to paper as well. Currently, FP8 training is popular, and DeepSeek released their whole infrastructure for training in FP8, but the next challenge is FP4, training neural networks with just 4 bits per weight. The new Nvidia Blackwell architecture supports FP4 training, and Nvidia did a lot of research and they wrote a paper on how to use FP4 training. So it consists of a bunch of tricks. So they use like 3, 4, 5 different methods all combined. It's very detailed, it's very fine-grained. So you need to apply different methods for different situations. It is a bit more complex than just putting the whole thing or almost whole thing into FP8. But with this tutorial, you will understand everything. You also have this button here to copy entire blog, and you can paste this into ChatGPT or some chatbot and then chat with it, ask questions. So this is for self-studying. It's very good. You can also copy this with Control-A and copy everything. Prerequisites for this tutorial. You need to know about numerical precision, like FP32, BF16, FP4, like what do they mean? You can watch YouTube videos, or you can copy this whole thing into ChatGPT, as well as this. It's good to know about quantization and dynamic ranges, but this is the main thing you need to know. So the main thing is the problem with outliers when scaling. So I'm going to explain this now. So let's say you have some array. It has these numbers, and you see number 50 is a lot larger than all of these numbers. Now this is the thing. In FP4, so with just 4 bits, in this exponent 2 mantissa 1, so you use 1 bit for sign, 2 bits for exponent, and 1 bit for mantissa. So you should this is a prerequisite for you to learn on your own on YouTube, or if you don't know what this means. So it's this prerequisite here, numerical precision. So you can only represent these numbers here, so plus or minus, well, 0 is not plus or minus, so 0.5, 1, 1.5, 2, 3, 4, and 6, and plus or minus. So only these numbers. So when you have these numbers here, you need to scale them to represent them with these numbers. So this is the other prerequisite. How do you scale numbers? But I will explain now. So we have this array. We're going to find the highest number here, 50. And we will divide 6, which is the highest representable number in FP4, with 50 to get the scaling factor. And we will use this scaling factor to scale this into FP4, NVFP4 range. So we can do multiplications and stuff with FP4, and then we will save this scaling factor to later return the numbers to their original scale. That's how we will represent this array in FP4, and then do multiplications and then return it back. So using this scaling factor. The reason we take the highest number is so we can fit, we need to squash entire scale, entire array to this 6 to minus 6 scale. So we scale the highest number to be 6. And then if the highest number becomes 6 or minus 6, depending on if the highest number is positive or negative, because we look at the absolute value of the highest number. So we find the highest number. So if this was minus 50, this would still be the highest number. So then it would just be mapped to minus 6. So we map that highest number to 6 or minus 6, and then we scale down all of the other numbers with the same scale to keep them like related to each other. Now this is the problem. When you map this to 6, and when you use this scale of 0.12, which is how much you need to multiply this 50 to get the 6, then you get these numbers that are very close to 0 for every other number. Because this is a big outlier, and this is the problem with outliers. When you get these numbers, what you need to do is you need to map them to the closest representable number. So this is closest to 0. This one is also closest to 0. This is also, all of them are closest to 0 out of these numbers here. So then all of them would become 0. And then we lose information. So once we want to get them back later, they would all map to the same number, but there is actually difference. So now we lose information because of this outlier provides such a huge scaling factor that all of the other ones get mapped to 0. So you want some techniques to deal with these outliers. So this is kind of the prerequisite you need to understand. So you can copy this, ask ChatGPT, or watch YouTube videos if you don't understand this. This is for self-studying. Now that we went over these prerequisites, let's see the paper. So we get 2 to 3 times increase in arithmetic performance, which is actually the matrix multiplications, and a 50% reduction in memory usage. First, when scaling down the arrays with the scaling factor, they are applying it to 2 separate things. So firstly, they are applying it to an entire tensor. A tensor can be all of the activations of some layer, maybe some dense layer or some output or inattention mechanism. Or tensor can be like a set of weights, maybe weights that transform, like vector embedding onto key embedding, or the key of that token. So anyways, these weights or these tensors can be huge. They can have millions of values. So they're going to have a certain scaling on this entire tensor scale. They will scale the entire tensor. Below this image that we will come back to, I wrote some examples of tensors and activations. And they also have a scaling per block, which is a very small block of just 16 contiguous numbers next to each other. So these big tensors would be partitioned into thousands or millions of these small blocks. And these small blocks are where the main scaling to FP4 happens. And we will see what that means. First, per tensor scaling. So a single scaling factor is calculated for the entire tensor, entire set of weights. And so based on the maximum value of absolute of that tensor. So it can be like the biggest number, does it have plus or minus, doesn't matter, as I explained earlier. And this scaling factor is saved in FP32, very high precision here. If we go back, I want to remind you, scaling factor is this 0.12 when you are scaling the big range, or you can also have a range that's smaller, that's not 6 to minus 6, that's like 3 to minus 3. Then you need to stretch it to 6 to minus 6. So you want to always like put the range between 6 and minus 6 when you go to FP4. So when you store this scaling factor in a high precision like FP32, then you have a very precise scaling back to the original tensor. And if you store it in smaller precision like FP8, then you're going to lose some information on this scaling factor. So when you scale back the numbers, they're not going to be so accurate. But since here we are scaling entire tensor, huge number, we just use a single FP32 memory slot to save this scaling factor, and we will have only a few of those. And so we will not take a lot of memory with these scaling factors, because one scaling factor is applied across so many numbers, millions of numbers. And when we go here in the fine-grained scaling per block of 16 elements, then we will save that scaling factor to FP8. We will have a lot more of these scaling factors. So FP8 helps us not use too much memory for scaling factors, because there will be so many of them, so many blocks of these 16 elements. So why do we need to scale it 2 times, not just once? Because in this fine-grained scaling, when you when you use FP4 to store and FP8 for the scaling factor, this also has a limited range. So the maximum combined values you can represent here is from minus 2688 to 2688. So those are the numbers you can represent with FP4 and FP8 scaling factors. So we need to first get entire tensor into this range. And so we will do that with the first scaling. Another advantage in using just 16 elements per block, and so just scaling 16 elements to FP4 and having a single scaling factor for 16 elements is when you have a huge outlier, it will only mess with the other 15 elements within that block that have the same scaling factor, but it will not mess with other numbers in other blocks because they have different scaling factors, so they are separated. So this kind of isolates the issues of huge outliers. So for example, if we had 32 elements, then single outlier would be messing up with the bigger block. Here we see what the new Nvidia Blackwell Tensor GPUs support, what kind of formats. And we're using this NV FP4, so exponent 2 mantissa 1. We kind of see the speed up over BF16. And these are actually good GPUs. I think these are better than H100, H200. So 4 times, 6 times speed up. This is a bit of foreshadowing the techniques that we will discuss. There is 1, 2, 3, 4, and even more other techniques other than ones that I just explained. And in this graph you want to be as higher as possible, so the red one is best. It's most similar to just training in BF16. But we will see what these techniques are. And you see, every time you apply one of them, you get better and better results. Then we have this image. So we don't want to quantize the entire model, everything in FP4. We want to keep some of the things in BF16, FP16, FP8, and we need to see which things are important to keep. So this graph is a bit tough to understand, so let's go down below. This is what we will do. We will use NVFP4, which is our FP4 format that we are using for the majority of general matrix multiplications within the linear fully connected layers. But final layers of the network are most sensitive, so we need to keep them in BF16, not in FP4. So keeping the last few layers in a neural network or blocks in the transformer architecture in BF16, then that is sufficient to ensure stable training. We'll see more. There are also some components that we always want to keep in BF16 or 32, not just in last blocks or layers. So those are embeddings, so word embeddings, token embeddings, the dictionary, output projection head. This is the last thing after all of the layers of the transformer. This happens just once. Normalization layers, so I guess these are RMS norm, layer norm, batch norm. Non-linearities, I think they mean activation functions. We need to maybe check the paper for this one. And then most part of the attention mechanism like softmax. Although this may seem like a lot of things, the biggest parts are still kept in FP4. So the huge general matrix multiplication in the feed-forward layers, in the mixture of experts in experts. So those are the biggest memory eaters and compute eaters, and they go to FP4. And then inside of attention mechanism, some parts as well. So here we see interesting graph. The black line shows if we just do entire training in BF16. So this is the best validation loss in the end, but it's the most computationally expensive. So if we keep all of the layers, all of the linear layers except last in FP4, then the validation loss kind of explodes, so model doesn't learn. Last two layers in BF16, it learns better, but also here explodes. But then first two and last two layers, now it doesn't explode, now it learns. And the green is last four layers in BF16. So this actually works even better. And these first four layers in BF16, this goes crazy immediately. So this doesn't work. Next trick, random Hadamard transforms, RHT, for outlier management. So this is just a trick. If you have some matrix such that that matrix times itself gives identity matrix. We call that matrix orthogonal. I'm just explaining the prerequisite for you to understand what they do. So if you have activations times weights, if you actually multiply activations times our orthogonal matrix and then orthogonal matrix times weights, this will not change the result of this activations times weights because this is in here identity matrix. But what this helps us do is deal with outliers. So let's say these activations, let's say it's like this array, very small array, and we have huge outlier 30. When we multiply it with some age matrix, this is not a learned parameter, this is just set by engineers, a value of this, then we can transform this array with huge outlier into this array that's actually more, that doesn't have such huge outlier anymore. So this is what happens by multiplying activations in this example with this age matrix. We remove the outlier. And then same matrix times weight, so we don't change the result. This is an example of this matrix age that can be used, and engineers are setting this hard coding. This is not learned. So this matrix is not applied everywhere. The paper found it was most critical for stability when applied to weight gradient calculation. This is the part of the backward pass where the model calculates the updates for its weights. And applying it elsewhere provides no benefit and could even hurt performance. They tried on gradient with respect to weights, forward propagation, and gradient with respect to inputs. And on this graph, you want to be as high as possible. Here, the green one, applying it to weights with respect to a gradient with respect to weights yields best results. And you see that applying it nowhere, the black line, still better than applying it to forward propagation or gradients with respect to input. It's important to also find the right size of this age matrix. Larger matrix deals with outliers better, but it's more computationally expensive, and the paper found that 16 times 16 matrix provides the best trade-off with strong outlier mitigation while minimizing compute overhead. Here you can see that 4 times 4 matrix is too small, and then 16 times 16 performs very similarly to 128 times 128, but this one is a lot harder to compute, so they just are gonna use 16 times 16. Now there is an issue that can happen in some edge case with this matrix. If you have some block of data and it's positive, positive, negative, negative numbers, and in your age matrix you also have that pattern, so you have positive, positive, negative, negative. When you multiply these matrices and these rows, this can actually create even bigger outlier, because they are all added up. So there is a fix for that. You can randomly flip signs of the age matrix, and now it's not gonna give a huge number. It's not gonna become an outlier. And you can just randomize these signs once and then reuse it for entire training, and it works. You see here that randomizing it once, green, and randomizing it often, blue, yields same results, while not randomizing it creates worse results. Next problem or issue. So imagine we have a matrix. Let's say this 2 by 2 matrix. These are neural network weights. So we apply our block scaling. So let's say we just scale the first block with some scaling, the first row with some scaling factor, and then the second row with some scaling factor. The issue is in the backward pass, this weight matrix will be transposed. So now when we want to return those scales back, we're gonna apply to the row, but the rows are now the columns, so we will apply to the wrong numbers the scaling factor. The solution here is to actually have the whole 2 by 2, the square matrix, have a single scaling factor. So instead of 1 by 2 We do 2 by 2, so we do the squares. Now, if they are transposed, they still have the same scaling factor. But this is only good. This should only be applied to weights, not to activations, because weights are persistent. You can read about it here. So weights are persistent, and as you train the model, this error accumulates. So you see here, the purple and blue is the big difference if you apply it properly, like purple, and improperly, the blue line. So this is what the error accumulation in weights during the training does. It ruins kind of the training. But activations happen just once during forward and backward pass, and there is no error accumulation. They are discarded after this forward and backward pass. So they are not so much so sensitive to the error. So we don't need to apply 2 by 2 or block size. In their case, they're using 16 times 16 blocks. So you see here, orange and red are almost the same. So applying it properly or a bit improperly has almost same results because there is no error accumulation. So main point is apply block size scaling to weights and this single row scaling to activations. Because weights are persistent and we need it to be accurate, and activations are discarded frequently, so there is no error accumulation. Next problem and solution. Let's say we have these numbers 0.6, 0.789, and we want to round them because we cannot represent these in FP4. So in FP4 we can represent 0, 1 or other numbers, but we want to round these. So if we round them just to the nearest number representable in FP4, all of them will be 1. The problem is the main value of this array is 0.75, but the mean value. And the mean value here is 1. So this creates a bias. So the trick is not to round it to the nearest number, but give it a probability. So this 0.8 has the 80% chance to round to 1 and 20% chance to round to 0. And this has 90 to round to 1 and 10 to round to 0. So over the long run, some of these will actually snap to 0, and so the mean will actually be 0.75 here as well. There is explanation here. The paper found that it was essential to apply this stochastic rounding when quantizing gradient tensors. But they also found that for weights and activations, in the forward pass, rounding to nearest is better, and stochastic rounding can actually degrade performance. So this is just experiments and ablations. So you don't want to apply stochastic rounding to weights. You see the loss absolutely explodes here. You don't want to apply it to activations either. But applying it to gradient with respect to weights with data doesn't explode and follows this BF16 training. So they use all of these tricks and trained it for 10 trillion tokens, which is a lot of tokens. And you see, it follows closely the FP4 baseline training, while being 2 to 3 times faster, taking 50% less memory. So here you see they marked transition from phase 1 to phase 2 of the data here, maybe a bit of loss spikes, although I don't think they are too big, and then start of learning rate annealing 20% before the end. Now the loss starts to go down a lot faster, and then this loss spike here is from transitioning from data phase 2 to phase 3. The accuracy seems to follow FP8 on these benchmarks as well. Now they compare different FP4 formats. So MX FP4, you see NV FP4, their format needs 1 trillion tokens, and for the same loss, MX FP4 format needs 1.36 trillion tokens, so this is 36% longer. And here at the bottom I have this coding exercise, and at the top here You can see this paper here, but implementation PR, this is the code, how they coded. There is a lot of code here, a lot of changes. So if you click this code exercises, I just told the AI to create some coding exercises, so you can check it. And maybe see you next time in the next video. Check out my last video, DeepSeek Sparse Attention Explained. It's actually a very good explanation of that as well.